are actually used for low power applications. Okay, where means where the load is basically not exceeding basically 5 kilowatt. Okay, so they are basically used for supplying small DC loads. Now above this we go for our these three-phase diode rectifiers. Now the reason being that there are several disadvantages of using a single phase AC to DC converters. Okay, what are the disadvantages? Number one is that the single phase AC to DC converters have large output voltage and current form factor. Okay, so because of this large output voltage and current form factor, we can very well understand that the rectification ratio or the efficiency of these particular rectifiers would be very less. Second, the single phase AC to DC converters have large low frequency harmonic ripple current. So this low frequency harmonic ripple current will be causing harmonic power loss, and again the efficiency would be decreasing. Okay, again if we have uh, studied the previous classes properly, then we have also found out that these single phase AC to DC converters are using very large filter capacitors. Why they are using very large filter capacitors? They are using very large filter capacitors for obtaining smooth output DC voltage. Okay. Moreover, what is happening is that low frequency harmonic current is being injected in the input AC line of the system, because of which this low frequency harmonic current is very difficult to filter. Okay. Yes, Partho, you have raised a hand. Any query?
No, sir. Sorry, sir.
Okay. So what I was saying, yes. So the single phase AC to DC converters are actually injecting low frequency harmonic current in the input AC line. Okay. So these are very difficult to filter in the input AC line, as well as the situation becomes very worse when we have capacitive loads. Okay, that is more number of harmonic currents would be introduced into the system. So many of these disadvantages are mitigated by using our three-phase AC to DC converters. Now these three-phase AC to DC converters are used for power output rating of higher than 15 kilowatt. Okay. So what are the advantages? The advantages is that these polyphase rectifiers produces less ripple voltage. Okay, it means less ripple output voltage and current compared to the its single phase rectifiers. Okay, and the efficiency of these polyphase rectifiers are also high, while the associated equipments required are pretty low. Okay, now in the figure that we have here, as you can see here, in the figure that we have here, we have shown a basic three-phase star rectifier circuit, which can be considered as three single-phase half-wave rectifiers combined together. Okay, this is a basic three-phase star rectifier circuit, which can be considered as three single-phase half-wave rectifiers combined together. Okay, so that's why it is sometimes also referred to as a three-phase half-wave rectifier. Okay, this is also referred to as a three-phase half-wave rectifier. Now, as you can see that the diode in a particular phase conducts during the period when the voltage on that particular phase is higher than the other two phases. Okay, the diode in a particular phase conducts during the period when the voltage on that phase is higher than that on the other two phases. Okay, this is how this three-phase rectifier should have worked. Now, I think we have the waveforms also. Okay. Yes. So as you can see that this is a typical waveforms for this three-phase star rectifier. Now this is the R phase, this is the Y phase, and this is the B phase. Okay. And with respect to this, the load voltage is also shown, which is the voltage that is across this load RL. Okay. Uh, Across this load R, actually resistive load. Okay. So as you can see, this is the voltage that we are getting, and also we can see the diode current. Okay, and this is, and the diode current that is being shown here, this is only for one phase. Okay, only for phase R it is shown. The same thing will be obtained for our phase Y, phase B also. Okay, so the current and the diode voltages that are shown, this is for only for the R phase. The same knowledge can also be extended for our Y and B phases. So it is very clear that here the conduction angle of each diode is 2 pi by 3, as can be seen from here. Okay, it is very clear that the conduction angle, okay, the conduction angle of each diode is 2 pi by 3. Okay, what was the conduction angle for a single phase rectifier circuit? If you recollect, it was pi. Okay, but here the conduction angle of each diode is 2 pi by 3 instead of pi. Okay, please remember that this star rectifier circuit is used where we require that the DC output voltage is low. Okay, and the required output current is large for a practical single phase system. Okay, I'm again repeating, this circuit find uses uh, what I just said, where the required output voltage, where the required DC output voltage, okay, is relatively low, and the required output current is too large for a practical single phase system. Okay, okay, now what we have, so we are taking R, this as you can see, the taking the phase R as an example. We are seeing that the diode, we are seeing the diode conducts from which point to which point. As you can see, the diode is conducting from pi by 6 to 5 pi by 6. Okay, taking the phase R, okay, as an example. Now, as we have just said, that the diode in a particular phase conducts during the period when the voltage on that phase is higher than that on the other two phases. So, as you can see here, at this portion, at this portion, this voltage is higher. Okay, this VRN is higher compared to the other portions. Okay, this VRN is higher compared to the other voltages, and that's why uh, this diode is conducting. Okay, and that's why this diode is conducting. Okay, and when this diode is conducting, as you can see that, and when this diode is conducting, so this is the output that we are getting. This is with respect to the current that is flowing through this particular diode. Okay, it is flowing through this particular diode. Okay, and the voltage and the peak inverse voltage for this purpose, that is also being shown here. Okay, so what is the average value? So as you can see, the average value is written here. So the average value is given as VDC equal to 3 by 2 pi integral of pi by 6 to 5 pi by 6 Vm sin theta d theta. If we solve this one, we will getting this expression of VDC equal to 0.827 Vm. Okay, let this be our equation 1. Then what about our RMS value? So we have to find out the RMS value also. Okay, so the RMS value will be something like this. As you can see, that the RMS value of output voltage will be VL, which is equal to root over of 3 by 2 pi integral of pi by 6 to 5 pi by 6 Vm sin theta whole square d theta. Solving which we are getting it has to be 0.84 Vm. Let this be equation number 2. And in addition, the RMS current in each transformer secondary winding. Here, the RMS current in each transformer secondary winding is can also be found out by this expression of I is equal to Im, which is equal to 1 by 2 pi by 3 plus root over 3 by 4, which is equal to 0.845 Im, where Im is equal to Vm by R. Okay, so one thing is clear from these particular figures is that from one thing is clear from this particular figure is that the peak inverse voltage. Okay, as one thing is clear, that the peak inverse voltage, let me write it down here, that the peak inverse voltage of the diodes is equal to how much? It is equal to 1.73 Vm during the blocking state, as it can be seen from here. Okay, then the peak inverse voltage of the diodes is equal to 1.73 Vm during their blocking state. So if this is the peak inverse voltage, then obviously the peak repetitive reverse voltage rating of the diodes has to be higher than this 1.73 Vm to avoid reverse breakdown. Okay. I'm again repeating, the peak inverse voltage of the diodes is equal to 1.73 Vm during the blocking state. So the peak repetitive reverse voltage rating of the diodes must be chosen to be higher than 1.73 Vm. Okay. So again, during its conduction state, what we can see that the each diode has a forward current. Okay, each diode has a forward current. The figure that is being shown, this is for phase R. The same thing will be for phase B, phase C, and so on. We can also write it for phase B, then miss for phase Y, then for phase B, and so on. Okay, we can easily draw it. Okay, so what will happen is that, so as you can see that each diode has a forward current that is equal to the load current. Okay, each means each diode has a forward current that is equal to the load current. Okay, maximum is how much? Vm by R. So therefore the peak forward, so, and therefore let me write it down somewhere here. Okay, so therefore the peak repetitive forward current rating, the peak repetitive forward current rating, okay, of these diodes must be chosen to be uh, higher than the peak load current Im. Okay, must be chosen to be higher than the peak load current Im. So what about the form factor? So as you can see, the form factor of the diode is Is by ds, that is sorry, that is Is by IDC. Okay, so that is equal to 1.76. Then we have the rectification ratio, which is PDC by PL, which can be written as 0.968. Then we have the form factor of the three-phase half-wave rectifier. The form factor of the three-phase half-wave rectifier is equal to 1.1065, and the ripple factor of the three-phase half-wave rectifier would be equal to 0.182. Okay, it would be 0.182. Okay. Now we have talked about a three-phase start type rectifier circuit, correct? Now let us talk about a three-phase bridge rectifier. Okay, we'll be talking about a three-phase bridge rectifier. Now in this figure, as you can see in figure 3, we have a three-phase bridge rectifier. Now these three-phase bridge rectifiers, their common applications are obviously they are used for high power applications. Okay, so we can write that they are used for high power applications. Okay, they are used for high power applications. Okay, now why? Because they have the highest possible TUF or transformer utilization factor for a three-phase system. They have the highest possible transformer utilization factor for a three-phase system, and that's why the three-phase bridge rectifiers are very commonly used for high power applications. Okay, and they and obviously being a three-phase uh, diode rectifier. Okay, so these rectifiers are commonly used in industry to produce a DC voltage and current for large loads. Okay, they are used for commonly used in industry to produce a DC voltage and current for large loads. Now as you can see, if we apply the Kirchhoff's voltage law around any path, if we apply the Kirchhoff's voltage law around any path, uh, it will show us that only one diode in the top half of the bridge may conduct at one time. Okay, only one diode in the top half of the bridge, that is either D1, D3, or D5. Either one of them would be operating at one time. The diode that will be conducting will have its anode connected to the phase voltage that is highest at that instant. Okay, the diode that is conducting will have its anode, as you can see, have its anode means have its anode connected to the phase voltage, have its anode connected to the phase voltage that is highest at that instant. Okay, similarly, if we apply the KVL in the bottom half of the bridge, the KVL, when we apply the KVL at the bottom half of the bridge, it shows that only one diode in the bottom half of the bridge may convert AC to DC. Okay, so that particular diode is
স্যার আপনার ভয়েস আসছে না।
that is lowest at that particular instant. Okay, that is lowest at that particular instant. Okay, am I audible?
ইয়েস স্যার।
Okay, I think so. There were some network issues in my here. Okay, so the other things that can be inferred from this, is very clear that the output voltage across the load will, what it will be. So the output voltage across the load is one of the line to line voltages. Okay, the output voltage across the load will be, not will be, is, okay, is one of the line to line voltages of the source. Okay, so output voltage across the load is one of the line to line voltages of the source. So when D1, for example, when D1 and D2 are on, as you can see, when D1 and D2 are on, then the output voltage would be how much? When D1 on and D2 is also on, so the output voltage would be how much? Output voltage would be, it is VRB. Okay, the output voltage will be VRB. So what we are saying, that the output voltage across the load is one of the line to line voltage of the source. I think that can be understood from this particular figure. Okay, so what so what we can say, that the diodes that are on are determined by which line to line voltage is highest at that instant. Okay, so the diodes that are on are determined by which line to line voltage is the highest at that instant. So for example, for taking our example only, so when VRB is the highest line to line voltage, the output is VRB. Okay, when the VRB is the highest when VRB is the highest line to line voltage, the output is VRB. Okay, so please remember that this particular circuit, okay, this particular circuit, it can operate, it can operate with or without the transformer. Okay, with and without the transformer, and will give 6 pulse ripples on the output voltage. Okay, it will give 6 pulse ripples on the output voltage. We'll be seeing it here only. Okay, here as you can see also, it will giving 6 pulse output. Okay, in the output voltage. So 0 to 2 pi, as you can see, 1, 2, 3, 4, 5, 6. Okay, 6 pulse ripples on the output voltage. So how many combinations of line to line voltages we can get from this circuit? We can tell. So how many combinations of line to line voltages we can get? Anybody? We can get 6
9.
combinations. Six. Okay, 6 combinations. How? We are taking 3 phases taken 2 at a time. Okay, 3 phases taken 2 at a time. Okay, so 6 combinations of line to line voltages can be obtained. Okay, so 6 combinations of line to line voltages can be obtained, uh, where we have taken 3 phases taken 2 at a time. Okay, now considering one period of the source to be 360-degree, if we consider one period of the source to be 360-degree, uh, transition of the highest line to line voltage, the transition of the highest line to line voltage must takes place every 360 degree by 6, that is every 60 degree. Okay, so because of the 6 transitions that occur for each period of the source voltage, the circuit is called a 6 pulse rectifier. Okay, I'm again repeating, we are means there are 6 combinations of the line to line voltage. So what we are considering, so considering one period of the source to be 360 degree. Okay, a transition of the highest line to line voltage must take place every 360 degree by 6, that is every 60 degree. Okay, and because of these 6 transitions, okay, that occur for each period of the source, okay, the circuit is called, what it is called, what I said, it is called a 6 pulse rectifier. Okay, it is called a 6 pulse rectifier. Okay, so because of 6 transitions that occur for every period of the source voltage, this circuit is called a 6 pulse rectifier. Now, as you can see in this particular figure, that the diodes are numbered. Okay, and how they are numbered? The diodes are numbered in the order of the conduction sequences. Okay, and the conduction angle of each diode, let me write it down. The conduction angle of each diode is how much? It is 2 pi by 3. Okay, is 2 pi by 3. So what is the conduction sequences? So the conduction sequence is, so the conduction sequence we can very well understand what because the diodes are numbered in order of the conduction sequences. So the conduction sequence is how much? The conduction sequences for the diodes is 1 2, as you can see, 1 2 2 3 3 4 4 5 5 6 and 6 1. Okay, this is the conduction sequence. Now, as you can understand that the output frequency of the output voltage is 6 omega. Uh, what would the output frequency is? It is 6 omega. Okay, fundamental frequency of output voltage. কত বললাম? It is 6 omega. Where what is omega? Omega is the frequency of the three phase source. Okay, omega is the frequency. Omega is the frequency of three phase source. Okay, I think you can understand now. Okay, so now let us see the three phase bridge rectifier voltage waveforms. Okay, so as you can see, the voltage waveforms and the current waveforms are given. Again, this is the output voltage and this is the current for one sequence is given. As you can see here, D6 and D1 conducts for up to this portion, and from this portion our D1 and D2 is conducting. So as you can see that the line voltage is how much is line voltage? As you can see that the line voltage is shown here also. I'm writing is just it is equal to 1.73 times the phase voltage. Okay, The line voltage is 1.73 times the phase voltage of a three-phase star connected source. Okay, and please remember that in this particular circuit, it is permissible to use any combination of star or delta connected primary and secondary windings because the currents associated with the secondary windings are symmetrical. Okay, I'm again repeating, it is permissible to use any combination of star or delta connected primary and secondary windings because the currents associated with the secondary windings are symmetrical. So if any problems can be given, if any problem is given regarding this three-phase bridge rectifier, so the primary and secondary can be interchanged as this is the as the primary side being the star and the secondary side being the delta, and then the same bridge rectifier is given. Okay, these things can be done. So obviously there will be, you will be requiring certain transformer ratios, and depending on the transformer ratios you can easily solve the particular problems. Okay, so this is the typical waveforms, as you can see that we are seeing here. Okay, and this is the current waveform. So this is the line current, as you can see. Okay, so this is the line current. So the line current for each of the six diodes is shown here. So this is ID1, ID2, ID3, ID4, ID5, ID6, and this is the source current. See the how the source current is changing. So it is very well understood that that many harmonics has been introduced in the source current. Okay, now in what happens that in applications, in many applications a load with series inductance is used. Okay, so if that is the case, when we have a load with series inductance, okay, that means that the output is filtered and the result is as you can see here. Okay, so load with series inductance, load with series inductance results in a results in a DC load current. Okay, results in a DC load current, as you can see here. So what is happening that for a DC load current, the diode and the AC line currents are filtered. Okay, means the diode currents and the AC line currents are all filtered, as you can see when the output is filtered. Okay, and because of which we are getting something like this. Okay, so these figures are we obtained when the load is in series with an inductance, Okay, now what about the three phase power from the source? So let us write down the apparent power from the three phase source. Okay, let's write down the first point, the apparent power from the three phase source. What is the apparent power? It is actually can be written as S, which is equal to root over 3 V line to line RMS into I source current RMS. Okay, so uh, so what is the maximum reverse voltage? What is the maximum reverse voltage across a diode? It is the peak line to line voltage. Okay, the maximum reverse diode, the maximum reverse voltage across a diode is the peak line to line voltage. And how the periodic output voltage is defined? Actually, we may write it down that the periodic output voltage is defined by, let me write it down, is defined as, it is written as V0 omega t equal to Vm line to line sine omega t for pi by 3 less than equal to omega t less than equal to 2 pi 3. Okay, with period of 2 by 3. Okay, why we have taken a period of 2 pi of why we have taken a period of pi by 3? Just for the purpose of determining the Fourier series coefficients. Okay, So what I'm saying, the period are to be defined as V0 omega t equal to VML, means the peak voltage line to line sine into sine omega t. So basically we are taking this portion, that is from pi by 3 to 2 pi by 3. We are talking about our phase R here only. Okay. So let us write down the Fourier's coefficient then of the output voltage. Okay. So if so from the waveform it is clear that the waveforms are in symmetry, correct? So since the waveforms are symmetry, so the coefficients of the sine terms are zero for from symmetry. We can understand that. Okay, and the coefficients for the sine terms are zero. So the Fourier series, so the Fourier series for the output voltage can be expressed as V0t equal to V0 plus summation of n equal to 6, 12, 18 Vn cos of n omega 0 t plus pi. Okay. So if you do the Fourier series for the output voltage, why we have not taken the sine terms? Let me write it down, because uh, coefficients for the sine terms are zero for symmetry. Correct? We can write it down. Okay. Now, as you can see, then what would be the average or DC value of the output voltage? This one V0. So the average or DC value of output voltage V0 would be equal to how much? 1 by pi by 3 integral of pi by 3 to 2 pi by 3 Vm sine omega t d omega t. Okay. So if you solve this, this should be coming something like this. It is 3 Vm by pi. Okay. So this Vm, this is the what it is? It is the peak line to line voltage of the three phase source. Okay. So this can be written as how much? So this is can be written as root over 2 into VL RMS. Correct? This can be written as root over 2 into VL RMS. Okay. Now, what we are seeing from the amplitude of the AC voltage terms. Okay. So we can write that the amplitude of the AC voltage terms are how much? So R Vn equal to, if we solve this one, it should be coming out to be 6 Vm. I'm not solving it. I will be requesting you all to solve it. Okay. So Fourier coefficients, you have studied this one in your previous classes. So you can just apply the formulas. Okay. Where obviously not equal to, where this n is how much? N is actually 6, 12, 18 and so on. Okay. So as you can see that the output voltage is periodic with period 1/6 of the AC supply voltage. Okay, it is periodic uh, with 1/6 of the AC supply voltage, and the harmonics in the output are of the order of 6 kW. Okay, let me write it down. Harmonics are of the order of harmonics in the output, obviously. Harmonics in the output are of the order of what I said, 6 kW, where k is obviously equal to 1, 2, 3, and so on. Okay, and the output voltage, what I have said just now, let me write it down that also, that output voltage is periodic with period 1/6 of the AC supply voltage. Okay, this periodic with 1/6 of the AC supply voltage. So as you can see that what is the advantage of this three-phase rectifier over the single-phase rectifier? The advantage uh, of it over the three-phase rectifier over the single-phase rectifier is that the output is inherently like a DC voltage. Okay, that the output is inherently like a DC voltage, and this high frequency low amplitude harmonics, okay, high frequency low amplitude harmonics enables filters to be effective. Okay, high amplitude low frequency, uh, sorry, ultota hobe, high frequency low amplitude harmonics enables filters to be effective. Okay, I'm again repeating the advantage of the three phase rectifier over the single phase rectifier is that the output is inherently like a DC voltage, and the high frequency, low amplitude harmonics enables filters to be effective. Okay, so we have done the Fourier series for our AC voltage. For our AC voltage for our phase A, the same thing we can done. Uh, Not phase A, this is for the output voltage, and we can find out the Fourier series of the currents in phase A of the AC line. So this is the Fourier series, as you can see. Here also we have IA equal to 2 into root over 3 by pi into I0 cos omega naught t plus minus 1 by 5 cos 5 omega naught t plus 1 by 7 cos 7 omega naught t, and so on. So which consists of the terms at the fundamental frequency of the system, okay, and the harmonics of the order of 6k plus minus 1, where k equal to 1 to 3. Now, as you can see that because these harmonic currents may present problem in the AC system, filters are frequently necessary to prevent these harmonics from entering the AC system. Okay, so please remember that these harmonic currents may present problem in the AC system, and hence filters are frequently necessary to prevent these harmonics from entering the AC system. And these filters prevent the harmonics from propagating, or means these filters prevent the harmonic currents from propagating through the AC power. Okay, and obviously these filter components that we are always talking about, these filter components are chosen such that the impedance of the power system frequency is large. Okay, the filter components are chosen such that the impedance to the power system frequency is large. Okay, they will be affecting only the harmonic frequency. So if we have an RLE load, we have talked about how the equation is being developed for our RL for R load. The same expressions can be obtained for our RLE load also. Okay, so here we have a closed form expression of the R of I0. So as you can see that the closed form expression for I0 can be obtained for the RLE load. So for pi by 3 less than equal to omega t less than equal to 2 pi 3, for an RLE load, we can write that L di0 by dt plus Ri0 plus E equal to V0, which is equal to root over 2 into VL sine omega t. So the general solution can be found out as I0 equal to I1 into e to the power minus omega t minus pi by 3 by tan phi. I hope it is visible. Okay, here. Okay, plus root over 2 into VL, or we can replace it by VM also. Okay, is root over 2 into VL by Z into sine omega t minus phi minus sine theta by cos phi. Okay, where tan phi is obviously equal to omega L by R. Theta is the place where the line voltage is exceeding the battery voltage E, and Z is equal to root over of R square plus omega square L square. Now, as you know, that the current waveform is periodic over 1/6 of the input cycle. So it is periodic over 1/6 of the input cycle. So I0 at omega t equal to pi by 3 will be equal to the I0 at omega t equal to 2 pi by 3. Okay, here. Okay. I0 at omega t equal to pi by 3 would be equal to I0 at 2 pi by 3. So if that is the case, so taking this boundary condition into consideration, we can write down the expressions as we can write down these two expressions by replacing omega t equal to pi by 3, and here the omega t will be replaced by 2 pi by 3. Okay, and if we solve this one, so we are getting the expression for I1, and we will be putting this expression of I1 into here, and the total expression for the current comes out to be this. Okay, total expression for the current for a three-phase bridge rectifier comes out to be this. Okay, so with this we finish our today's class. The references from where I have taken today's class is given here. So will be you may use these three notes. It is available in the internet, so you can just use these three, and you will be able to understand these three-phase bridge rectifiers. If you have any problems, you may contact me later. I hope it is clear. Okay, I hope it is clear.
Yes, sir.
Okay, so thank you everybody. I am stopping the presentation. Rectifiers. Okay, so thank you everybody. You may leave the class.
Thank you, sir.